We'll use Monte Carlo simulation to verify the solution of a high school math problem. Here is the problem. There is a square, and inscribed inside the square there is a circle touching its edges, and inside that circle there is another square that touches the circle, right? So if we take the radius of the circle to be r, we can see the side of the outside square would be 2r, therefore the area would be 4r square. The area of the circle would be pi r square. And if we use Pythagoras theorem, we'll know if this is r, this is 90 degrees. This is going to be square root of r square plus r square, which is root 2r. And therefore, the area of the smaller square is 2r square. So the ratio comes to 4 is to pi is to 2. Today the motivation is not to prove it, rather use Monte Carlo simulation to see if this is indeed true, right? So with Monte Carlo simulation, we'll do random sampling and we will use about 10,000 points to plot it on a square, right? And to see how many of those points is on or in the circle and how many of those points are on and in the smaller square, right? So here are those 10,000 points, right? These are randomly generated points between 0 to 10, right? Okay. And what we're doing here is for those points we are inspecting for each of those points. If those point belongs to the smaller square inside, if point belongs to the smaller square inside, we give it a value 2, right? Similarly, if it doesn't belong to the smaller square inside but it belongs to the circle, that is it's outside the square, outside the inner square but inside the circle, then we give it a number 1, right? Give it a value which is 1. Similarly, if a point is outside the circle but inside the larger square, we give it a value 0, right? So there are 3 values, 0, 1, 2, distinguishing where the point belongs to, right? So with this we can actually calculate the ratios, right? How do we do that? Let's say if I just, when I hit F9, it refreshes all the values, right? The random values, right? It generates another set of random values. So each F9 is a new simulation, right? So let's say in this simulation, if I look here, right, out of the 10,000 points, all the 10,000 points, of course they belong to the big square because that's a superset. Now out of those 10,000, 7,800 points, 7,826 points would belong to the circle, and in this simulation 4,942 points belong to the smaller square, right? So if I see the ratios of those, you know, I can just divide 2,500 across. It comes to 4 is to 3.13, which is very close to a pi, and 1.97, which is very close to 2, right? So this is our actual number. This is pi, this is 4, this is 2. So the ratio should have been 4 is to pi is to 2. And when we simulate, it comes very accurate, right? If you see the accuracy, it's about 99%, right? 99.6, 98.84%. I can keep on hitting F8. I can see how it changes. Now one nuance that I want to show you here. Now for each, when we calculate all those points, right? If it's a 1, if it's a 2 or a 0, it should end here, right? As far as math is concerned, our calculation is in column D. We can just calculate the number of 1s, number of 2s, and number of 0s to come up with these values. But that's not good enough, because we want to show it visually, right, pictorially. And if you see how to show it, if I don't segregate those points, it will look something like this. It will look like 10,000 points on a 10 by 10 square, but you cannot distinguish which points are inside the circle, which points are inside the smaller square. Therefore, what I've done is I've segregated those values based on these numbers. I've segregated if it belongs to the smaller square, or if it belongs to the circle, or if it belongs to the outer square, right? So that way, and we can give it different colors. So it's a scattered plot. So 3 different scatter plots put together. They have each different colors. Therefore, you can see it, right? But the math here, while that's the visual, the math is confirmed here. Thank you.